Hey, hi, hello. Good evening to all. So, can someone confirm whether my voice is audible and you're able to see the presentation?
Yes, sir.
Yes, sir. Good evening. We can see the presentation. Yeah.
Yeah. Okay, so welcome back to the session. So, let's take a quick review of what we have, discussed in the previous session, and then we move on to the, you know, uh, neural network stuff. So, in the last session, we discussed so many things, right? So, why we need deep learning in general, how it differs from not differs. So what's the difference between machine learning and deep learning? So it is all about just extending the neural networks, making it deeper, and also coming up with different architectures. So it is simply a part of machine learning, and it is purely, as of today, is purely the learning is purely based on gradients, computing the gradients. Okay, and it is suitable for unstructured data set. So that is the key takeaway, and it so far the research is still there are a lot of research on how to make neural networks work well on structured data like tabular data. So if you're dealing with tabular data, you try with tree based approaches like XGBoost or something like that. Okay. So in this workshop we are going to stick with image data set. However, the concepts covered in the workshop, right, or in the bootcamp, whatever, could be extended to any data, any data type. But in the transformation step, like in doing a pre-processing or in representing the data, you may need to, put an additional effort in order to learn those things. Okay, so it differs based on the data type to deal with. Especially when you go to text-based data, then there are a lot of ways of encoding, words into vectors. Okay, and based on the problem, it differs. So text is quite complicated than images. Because in videos are more or less similar to images, but it takes a lot of computational memory. And speech is also quite different. Okay. And the first aspect is that whatever the problem you are dealing with, the first thing is to understand the data in its all aspects. Okay. So if you know more details, then you can do more, while you debug, if you want to improve the performance of your model, then having a good understanding of the data will always help you, not just about the algorithms, also about the data. So we discussed about how images are actually represented in a computer as a matrix. So if it is a binary image, these are all going to be, all the elements take only two values, either 0 or 1. If it is grayscale, then the elements, it is still a matrix, but the element values can vary from 0 to, say, if it is 8-bit, then 255. If it is a color image, then there will be three, matrices stacked on top of each other. So we call them as tensor. Okay. So especially when the image size becomes, larger, then you have to keep in mind about the, memory to store them, and also the computational aspect pitches in when you have lots and lots of images. Okay. And we introduced the concept of tensors. It's nothing but generalizing these arrangement of numbers. So you start with scalar and then vector and then matrix, but when we go beyond that, we have no name, so we simply call it as tensor. So we can start with scalar, we can say it is a scalar, but we can also say it is a scalar with tensor with 0 dim. And we say it's a vector, we can also say it is a tensor with 1 dimension. Then matrix, it's a tensor with 2 dimension. So when we go beyond that, we can say it's a tensor with 3 dimension, where up to this point we can somehow visualize this, but once we go beyond 3D, then we say it's simply a tensor with 4 dimensions. So when you say a tensor, the attribute dimension has to be associated with that, then only it makes sense. Okay. And any deep learning framework we prefer must provide a way to create a tensor and also provide efficient ways to manipulate them as well. Okay, so when I say manipulate, oftentimes we go and fetch some part of the tensor, right? So that accessing should be efficient, and then when we carry out some operations on them, that should be efficiently computed, right? And also when often, if one thing that you have to remember when you deal with deep learning framework is that most of the time when you reassign a variable, right? Say, let's say I assign a tensor to a variable x, okay, or identifier, whatever the name. Then if you reassign x to another variable y, then it is not a direct copy. We are not actually creating two copies of tensor, because creating a two copies takes, additional memory. So if you don't know what is going on there, most likely or most probably it won't make any copy unless you explicitly make a clone out of it. Okay, so most of the operation when you use this assignment operator is just a view, it is not exact copy. That you also keep in mind. And most of the commonly used operations are this flattening, reshape, transpose, all these things. That please refer to the documentation where you see exhaustive list of operations. You need not to go through each one of them, okay, in order to understand Pytorch. You only go through, I always prefer, right, you go through the code, and then if you encounter some new operation, then you refer to the documentation. Do not try to learn from, the documentation in itself, because it is really vast. And most of the time, remember that the Pytorch is not only for this classification problem, and the deep learning is not only for this text data, all these things. There are you can use it for reinforcement learning, and there are many types of learning. So Pytorch has to, support all those types of learnings. So the functions in the Pytorch, created keeping that in mind. So do not try to go through each one of the functions in Pytorch documentation. Okay, that's my advice. Okay, so then we also discussed all these steps. Finally, we ended up with, a basic computational unit of deep learning. Okay, so whether you are creating a multi-layer perceptron, or you are creating a convolutional neural network, or recurrent or transformer architecture, or you name it, whatever. Okay, fundamentally the computational unit is going to say that is a neuron. So what is a neuron? So a neuron is a computational unit that takes in an output and computes something and produce some output. Okay, it's a very nice definition. So the input to the neuron is often in the form of vector, but it could be matrix or whatever. So input is a tensor. We say input is a tensor, but for the sake of illustration, I am keeping as a vector. Okay, typically we I just comment. So I will find it. Are you able to hear me properly, or is it feeble?
Yes, sir. I mean, I have to max it out at my end. It's slightly feeble though. Maybe if you can get slightly closer to the mic if possible.
In fact, I actually the external mic. Okay, I just remove it. Now give me a second.
Or maybe if you use a headset, that would be helpful.
Okay, is that fine now?
Yes, sir. This is much better. Thank you.
Yeah, in fact, I didn't notice that the mic has dropped from my collar. Okay. Okay, so neuron is, a basic computational unit. It takes in a tensor as an input, but in generally we represent it as a one-dimensional vector. Okay, and let's start with the basic thing. We have a vector from x1. That contains elements from x1 to xn. Okay, it is simply, you can think of it as a n by 1 column vector. So here x1 to xn denotes a single real number. Okay, so we pack it as a vector. A neuron simply takes in this number and often associate, okay, a weight with this each of the element in the vector. Okay, we also denote weights by w. Sometimes this is called as weight, and also this is also called as parameters. Okay, so whatever that is learnable. So weights and parameters, we use these terms interchangeably, but this should be clear from the context. Okay, and these weights are multiplied with the elements in the vector or input, and then they are summed up. And in addition to this input, there is another input, we call that as a bias, and also associated weight with that. Typically, it is denoted by x0 and w0. Okay, so what do we do? So now I have some set sequence of numbers as input. With each element, I will associate a weight with it. I have to learn the values for these weights. Okay, so these are randomly initialized, and then we simply make a dot product. Okay, so I simply multiply x1 and w1, and then x2 and w2, and all the way up to xn and wn, and then we simply sum it up. Okay, this is a kind of dot product, and then after you doing all these things, we will end up with a single number. Okay, so after this summing up of all these stuffs, then we end up with a single number. Then we pass this number through some function. Okay, often the function is non-linear function. You could also linear function, but there is no reason. Once you use linear function, then the network becomes, can be boiled down to single. I mean, you can't use some sort of deep networks. It immediately becomes shallow if we use linear function. Typically, the function f is non-linear. Okay, it oftentimes you see it is a monotonic. It kind of monotonous function, but that is not necessarily the case. It could be anything, but it should be non-linear. Okay, so since it takes the single number as an input, then we also get a single number as an output. So you think of a neuron takes sequence of numbers and associate weights with each elements in the sequence, and then multiply and then sum up and gives a single number as an output. Okay, you call it as base. If the function is kind of thresholding function, then they for this reason people call this as activation function as well. Okay, so it's simply a mathematical function, but making an analogy between neuron in the brain and artificial neuron, they call this as activation function as. Okay, and yeah, so we use this y hat to denote that it is a prediction. So in the classification setting or in the regression setting, whatever, so it's simply, you can think it of as a prediction. Okay, so this is a pictorial representation. So if you are new to this neural network, then starting with the pictorial representation is best option. So once you get familiar with this pictorial stuffs, then of course all these things can be concisely represented using single equation, right? So entire process, you have w and you have x, make a dot product, and then you pass the result through some nonlinear function. Okay, and just ensure the dimensions. Finally, you end up with single number. Okay. So now I have an input, right? So you just, I believe that you know what are supervised learning, all these things. Okay. So in supervised learning, what we have is there anyone who doesn't know what is supervised learning and what is training example, all these things? Can you put that in the chat? So I'm assuming you know all this, because I have seen some students are from foundational course. Okay, I'm not seeing anyone in the chat. Okay, so typically, right, in the supervised learning setting, we have a pair where we have an input x, and also based on the problem, here it is a classification problem, and then we have associated label y. So we call it as label or target or ground truth, different terminologies, but typically we have x and y pair. So x is an input to the neuron, and neuron gives some output. Okay, then we denote this as a prediction y hat, and then I have the respective ground truth or the label for it. Then we just try to make or measure how good our prediction with the true label. Okay, so of course you can do that by computing the accuracy, all these things, but the loss function, right, measures how good the neuron's prediction for all the training samples. Okay, we measure it. So the loss function takes only two inputs. One is the prediction, the other one is the ground truth, and there are variety of loss functions. Okay, so if it is a classification problem, if it is a binary classification problem, then we can use log loss, log likelihood loss, and then even if it is a multi-class classification, we can use negative log likelihood and cross entropy. Okay, typically we go with cross entropy for various reasons. Okay, so if your problem is classification, whether it is single label or multi-label, if it is a classification problem, the best loss function that captures, okay, the difference in prediction is using cross entropy. Of course, you can use mean square error as well, but the way it captures the difference is totally different from the way the cross entropy loss captures the difference. So to get a good performance in the real world, if you're using classification, if you're solving a classification problem, then use cross entropy loss. Okay.
Sir, can you change the pencil? Like,
you mean change the color, or what is that?
no, it's too thick.
I don't think I have a control on thickness. I'm not sure. No, it's not there. So that's the problem with the slide.com. So even in Zoom, I'm not able to write. So I thought, is typically you can scribble using features from a Zoom, but unfortunately, I'm not able to see that here.
So there's the scratchpad feature, right? Should get it there.
Yeah. So I was looking for that one, but it is not.
I think you will get a whiteboard, something like that.
Yes, you're exactly right. But it is not. So if I share whiteboard, I think the slide will disappear. So there is something called as whiteboard. But the moment I share it, then the slide disappears. But you can. Okay, so please bear with that. So if it is not readable, maybe you just let me know. So I try to write it concisely. Okay.
Sure, sir. Please continue.
Yeah, so it is cross CROSS. It's very difficult, by the way. Entropy. Okay. Loss function. Yeah, so whether it is a single neuron or network of neuron, okay, this is the setting. So we have an input and the network makes prediction, and then we compare how good the prediction made by the network to the actual ground truth. So for that comparison, we have to pick up the right loss function. There are many. Maybe you might have studied cross entropy in a different setting. Okay. So there are many loss functions that you should learn, and you have to pick the right one based on the problem you are dealing with. But if it is a classification, it is cross entropy loss. Okay. So once I measure the loss, what should be the next step? I know that we are going to initialize these weights, right? Randomly. That is the case. So if it is a single neuron, we have some n weights. But if I have network of neurons, then I have millions of weights or parameters. All of them are initialized randomly. Okay, so randomly in the sense, oftentimes it is, there are many ways of initialization, but here just assume that it is a normal distribution. Okay, so the weight values take values between say -1 to +1, for example. Okay, it is not too big. So the values are restricted. It is often near 0. Okay. So since all these weights are initialized randomly, then my prediction is not going to be, so good during the first iteration. So I measure the loss, and of course, obviously, we expect the loss should be higher. Okay, in the first iteration. Then now the core step is that I have to change my weights. So the only thing I can control in this entire stuff is that I can't control the input X. That's not in my hand. I can do transformations, but I can't modify the values in the sense it helps me in the final prediction. And I can only control these weight values. Okay, which means I have to come up with a right set of weight values or the parameter values so that the prediction becomes closer to the ground truth, not just for the training samples and also for the test samples, or even from the generalization perspective, it should perform well. Okay, so how do I do that? So in order to find the right weight values, okay, we have to compute some parameter, something called as gradient. Okay, essentially what it does is each weight value, right? The loss is influenced, the final loss values influenced by these weight values. If I change the weight value, of course, it will directly influence my final loss value, okay? Because I can, x1 to xn are fixed, I can't change that. But if I change weights w1 to wn, even if I do that randomly, then loss will go up and down for various values. So which means I want to compute how sensitive my loss function to the given weight value. Okay, for each weight value, I compute that, how sensitive the loss is, whether it goes up or down. Okay, of course, there is a, it's not by random choice. We have a way to do that using something called as gradient descent. You might already be aware of that. So we use the same concept called gradient descent in order to find the right direction of weight values in the parameter space. This is for single neuron. So once if we this is true for the entire network as well. If I have millions of parameters, then I compute the gradients for each parameters or each weights in the entire network. If I have billions, right? Typically, you might have heard this ChatGPT, all these neural networks with 175 billion parameters, right? For all these parameters, we need to compute the gradients. And fortunately, backpropagation works for all. If you scale up the network, backprop still works, okay? So once I compute the gradient, then I have to change the weight values, right? So I am just computing how sensitive the loss is with respect to the particular weight value. Then after I'm measuring it, then I have to make use of this gradient in order to update my parameters, right? So for that, we have this update. So this single rule is, okay, computing the gradient and updating the weight is the engine of all the neural networks. So everything boils down to these two steps. You compute the gradient and update the weight. Do this
Hello, sir.
iteratively. Yes.
So the gradient should be taken with respect for the loss function, right?
Yes.
So like we take the gradient of loss function with respect to W, the weight
Yes.
vector.
Yeah.
So here it's gradient of weight vector instead.
Yeah. So this is the notation we follow. It's actually I put the suffix as well, L, to denote that the gradient is computed with respect to the loss function. Sorry, this is what we follow in the lecture. So I just, in the lecture, we inform that this is the notation we are going to use. You just keep it in mind. It is with respect to the loss function.
No. What I'm trying to say is we compute the gradient of loss function, not like with respect to the loss function. Like what I have studied in MLT, in week 12, it was explained that the gradient of loss function is taken with respect to the weight vector, and it doesn't make sense to take a gradient of weight vector, right? We take a gradient of a function with respect to a vector always.
Yeah, that's what I'm saying. It's a gradient of, see, I have written this, right? Gradient of W with respect to the loss function.
That is the opposite thing, right?
Means that it should be opposite. Compute the gradient of loss function with respect to W.
Yeah. Sorry. I have to switch these terms. Yes, it makes sense. Gradient of loss with respect to W. Yeah, that's correct. This is wrong. Yeah, I have to change this. Okay. Oh, thanks for pointing that out. Yes. So we have to compute the gradient of loss with respect to the weight for each weight values. And then we have to use this learning rate. Okay. So we have different optimization algorithm as well. So in all the optimization algorithm, this gradient place is an input, and then somehow we make use of the current gradient as well as the history of gradients to come up with different optimizers based on the problem we deal with. Okay, but anyhow, the fundamental weight update rule remains same. Okay, so this is an, iteratively, all these weights are updated until the loss value typically never goes to 0, but as the loss keep decreasing, and we also observe how the accuracy, of the model increases. Okay. Yeah. Yeah, so there are various ways of checking the performance based on, once again, the type of problem. Yeah, typically, so now we have an image. So the straight question is that we have an image in 2D shape. Then obviously, if I want to make use of this image as an input to the neuron, then one straight approach, even though people won't do that, but one straightforward approach is to convert that into or flatten it out into a vector. Okay, but this might have some lot of redundancy when you do that. So typically what happens is that people compute some sort of features on this vector, and then they reduce the dimension, and then that's the traditional approach. Reduce the dimension and then feed those features as an input to the neural network. But again, just for the sake of illustration, we can feed in the raw value and let the network learn which pixels are playing the major role. Okay. And if you are using this multi-layer perceptron, this is how we go with. Even if we extract the feature, once again we end up with maybe a small vector instead of this big vector. But one problem with this entire approach, whether you are computing the feature out of this flattened vector or you are using this flattened vector as is, somehow we take the spatial correlation, right? The moment you break down this matrix into a vector, then this spatially correlated information is lost. So we want to retain this spatial relationship, and then we have to make use of a neural network to capture this spatial relation as well. And one more bigger problem is that if my image becomes, right, let's say 100 by 100, then when you flatten this out, then the size becomes 10,000 by 1. Okay, then I need to use, say, for example, 10,000 parameters for each pixel. Oftentimes it is found that it's not necessary. So people come up with convolutional neural network. Okay, so where the concept of weight sharing was introduced. Yeah, I see someone raised their hand.
Yeah, so just one quick question. What did you mean when you said spatial information? Are you referring to the spatial arrangement of the pixels themselves, or is it something else?
Yeah, that's exactly what. So when you take this out, right? So when you flatten this out, then typically in natural images, right? So if let's assume this portion is sky, okay, and these
Okay.
pixels are highly correlated. I mean, correlated in the sense, if it is blue, then the next pixel value is most likely will be blue. Okay, but when you break this out, what really happens is this relation is lost.
Right. Yeah, got it.
Okay, so that's why we go for CNN as well. Okay, one is to reduce the number of parameters, and the other one is to retain this spatial relationship, especially when we go with segmentation problem. Okay. Yeah, so if you refer to the literature, I think as of now, maybe some 50 plus activation functions are there. People come up with different types of, even they create their own activation function if the existing activation functions do not work. So typically, most often we start with ReLU in the case of CNN, but if you go to transformer architecture, then there are varieties of activation functions. Okay, sigmoid and tanh you might already know, and ReLU, leaky ReLU you might already heard of, and Softmax is also that I will talk about soon in the next 10 or 15 minutes. Okay, and varieties of or variants of ReLUs like leaky ReLU, all these things. Okay, but the immediate question is why we need different types of activation function. Why don't I just use sigmoid? Okay, people had been using sigmoid function almost for 2 decades. Only after 2006 or 7 they realized the problem with the sigmoid, then they changed the activation function, especially in the AlexNet, if I'm not wrong. Okay, so now if you look at closely, if I want to build a neural network, then I have a lot of choices. Okay, one is choosing the number of, yeah, I just introduced the a single neuron. So even in creating a neuron, I have a choice in, I have to make a decision which activation function is suitable out of some 10 to 20 activation function. And then we have to make a decision on the loss function. This is true in general, which loss function is suitable for this particular case, and which optimizer. Okay, so if our image, especially let's say we are dealing with sparse images. Okay, in the case of digits, let's assume in digits, when someone write a number, the background is almost black. Most of the pixels are black. The foreground is number. Okay, 1, 2, 3. So these sort of inputs are really sparse. So in such a case, using different optimizers, something called as ADAM-W or ADAM optimizer, they are really good at dealing with these sort of inputs. And again, we have a design choice, which optimizer is, once again, these are all kind of educated guesses. Okay, we can't give any guarantee. If you use ADAM, it quickly converges. Okay, but you can start with SGD and see how it works. If it doesn't work, then you may start with ADAM, and then you can experiment with it. And finally, of course, the learning rate schemes, all these things boils down to different design choices. Unlike in machine learning course, right, where we can do this hyperparameter search, but when you have deep learning, hyperparameter search is really costly. So people won't do such search. If your problem is really big and you are dealing with really big data set, then if you have enough compute, you can do that, but that's not advisable. So we have people come up with different types of learning rate schedulers, okay, based on extensive experimentation. Okay, we may stick with the literatures in such cases. Okay, so before moving on to the neural network, then we just talk a bit about why we need different types of activation functions. Why don't I just use sigmoid? Okay, so the answer lies with, we said it's deep learning. So in deep learning means we are making the neural network really deep in the sense, instead of having two or three hidden layers, we are making it some 150 hidden layers. Okay, 150, I won't say it's a hidden layer, 150 layers. Okay, so when we do so, we are computing the gradient with respect to the loss. So the computation of gradient starts all the way from the loss. First, we compute the gradient of loss with respect to the prediction. Then we make use of that and then back propagate that gradient all the way up to the first layer. Okay, so for learning to happen, all the parameters in my network has to receive the gradient, right? Gradient of loss with respect to that particular weight. So if it is not able to receive that gradient for some reason, then it won't learn anything. Okay, so here learning is defined as updating these parameters with respect to the gradient. If the gradient becomes 0 for some reason, then there is no learning. Okay, so but if you use sigmoid function, that's what really happens. So if we use sigmoid function in a really deep network, then the first, maybe the front layers, like first layer or second layer, they won't receive the gradients. Okay, so why is that the case? So I just talk about that a bit. I'm not going in detail once again. The primary reason is these sigmoid functions are saturated, right? So they have some values, maybe let's say it's from -1 to, I'm just writing. If we have some input values 10 or -10, okay, so the output in this case becomes 1, in this case it becomes 0. Okay, so if you closely look, the region is saturated region. Okay, I mean the output is kind of capped. So when we compute the gradients, essentially I have, we compute Wx first. Okay, then output from Wx will go as an input to activation, right? Let's say even if I have a single neuron, then after computing this dot product, I have a single number. Let me represent it by Z. Then this number, based on the value of this number, the activation function gives me some output. Okay, if the value is too high, it could be, let's say it is approaching really big value, let's 10, 20, even 10, 20 are really big, because my weight can, push these values. If it is not properly initialized, then this multiplication might gives rise to different range of values, right? -10 or +10, whatever. So in such a case, forward propagation, it doesn't matter, but during the back prop, right, the gradient with respect to the loss flows here. Okay, let's say I'm receiving the gradient from the previous. I assume that you know what is neural network. So let's say I have a layer 2 here. I am receiving a gradients from layer 2. Then this gradient has to go through this activation function first in order to compute the gradient with respect to the gradient of W. Okay, so once again, maybe my words are not properly arranged. So it's a gradient of loss with respect to W. Okay, so in such a case, if you take the derivative of this sigmoid function, okay, so you might see something like this. Okay, the gradient becomes 0 after some range of values. Okay, so and the maximum value of this gradient is also about 0.25. Okay, so if my input gradient values, let's say 1, but when it goes through the sigmoid value, then the output from this sigmoid value, the gradient of this sigmoid will be squashed, right? So it's 0.25 times 1, so it becomes 0.25. So if I keep on repeating this, okay, 0.25 times again 0.25, then it becomes 0.125. So if we have more number of neurons in the network, and if you are using sigmoid across.
Excuse me, sir.
Yes.
Sir, please reduce the size of pencil. It's very much big and words are not clear.
That's an unfortunate thing. I'm not able to do that. I don't think I have that option.
Sir, if in the menu.
Yeah, maybe you can check the menu. Yeah, here.
Yeah, so if I do that, right?
I think you can zoom out the page, whole page. That could help.
No, it's not working.
So there is another alternative that I may suggest. If you can go to Excalibur, you can use it on a separate tab. So you can just switch between tabs instead of drawing here. Okay, so you mean some whiteboard stuff?
Yes, here.
Yeah, excalibur.com.
Sorry, yes.
Excalibur, EXCALIDRAW. Excalibur.
I'll
type it in the chat box. Yeah, I'll type it in the chat box.
Aditya, can you please go on mute, please?
Okay, these ones. So do I need to sign in, or it's kind of straightforward?
It's straightforward. No need to sign in. You can just start drawing. Just click on the pencil tool and start drawing.
Okay, is that visible at your end?
Yeah, it's visible, sir.
Okay. So yeah, so since it's important, I'm repeating this again. Okay, so let's.
There's a line tool if you want to use it.
Sorry. Okay. We can draw that. I think this is fine, right?
Much better.
Okay, I'm not able to do that. How? Maybe I flat. Okay, let's say it's an sigmoid. Okay, you know how it looks. It's a kind of
yes,
S
sir. Yeah,
okay.
Yeah.
So when you take a derivative of the sigmoid, let's write this as sigma of x. Is that fine now?
Yes,
I mean,
clear.
Yes, sir, it's fine. It's clear.
Okay. So if you take a derivative of this activation function, okay, so we make use of this during the back prop. Okay, during the forward prop, it's fine. So even functionally, right, analytically, if you take a derivative, it is going to be sigma of x into 1 minus sigma of x. Okay, for a sigmoid activation function. And we know the maximum value of the sigmoid function is 1. So if my sigmoid outputs 1, okay, the activation in my neural network, if any neuron outputs the value 1, then during the back propagation, you can see that I put here 1 here, and then it becomes 1 minus 1, and then the entire thing becomes 0. So when it outputs 1, so if my input to the sigmoid, right, let's say it is z. If my z value is above, I just assume that if it is 10, okay, then my sigmoid outputs value 1. During the back propagation, the gradient has to flow through this sigmoid. And what happens is that the derivative of the sigmoid for this particular output is 1 and then 1 minus 1, 0. So the derivative becomes 0, which means the gradient won't flow through this activation function. Okay. And how, the input is controlled by this W and X, right? You can write Z, which is equal to W times or W transpose X, the linear part of the neuron. And then this Z is actually an input to the sigmoid. Okay. So if my Z value takes either larger value, let's say maybe 8 to 10, or very small value, let's say -8 or -20, something like that, then you can see that in both cases, if it takes larger value, then it outputs 1. So if the activation or if the sigmoid output is 1, during the back propagation, the gradient becomes 0 because of this equation. If on the other hand, on the other extreme, if my input is -8 or something, then the sigmoid output is 0. And during the back propagation also, the gradient becomes 0 in both the extreme because of this saturation behavior, right? Which means it essentially blocks the gradient flowing through this activation function. So if the gradient is not right in all the activation, we always receive the gradient of the loss with respect to some value in the previous. It's simply the gradient of the loss keep on flowing. So it has to flow through this activation function in order to reach this W. But because of this nature, this gradient will get multiplied with 0 or even near 0 values. Even in the good case, okay. Yeah, I maybe pictorially draw this. You see something like this. So the maximum value of the gradient you can see from this equation as well. Okay, the maximum of the value of the gradient is 0.25. So what does that mean? Even if my loss, the gradient of the loss is 1, that is coming to this neuron, but when it actually allows this gradient to my weights, it actually scales this down. Okay, so it only sends this 0.25. So which implies that if I have some 10 to 20 neurons connected together sequentially, and because of this scaling down nature, okay, after flowing through some 5 to 6 neurons, my 7th neuron will receive 0 gradient because of this nature. Okay, it's scaling down. So in both the settings, okay, when the input to the sigmoid is really big so that it reaches the saturation region, it won't allow the gradients to pass through it. And on the other extreme, even though you take control of, okay, by properly controlling this W, you can somehow control the input to the neuron falls in this region. Okay, you can do that. But even in that case, during the back prop, all the gradients will be scaled down by this 0.25 factor. 0.25 or 0.5, I'm not sure. Okay, but anyhow, it's not 1, so it will scale down. Okay, and if we have more number of neurons, eventually the last neuron won't receive the gradient. Okay, so what really happens is that now this is true even for tan H activation. Okay, because once again tan H, you can see it is also saturated, even though my input and output is 1 and -1, still has this saturation region. So we need to come up with different activation function. So we notice it that this problem is due to this saturation nature of the activation function. So people simply come up with a nonlinear function which is not saturated. Okay, it's simply, this is really good because if you take a derivative of this, then it is going to be a kind of step function with 1, which says that whatever the gradient it received from the previous layer, it simply passes it to the next layer. You mean to the weights? Okay.
So the first problem you described, is it that's called the Is it the one which is called the vanishing gradient problem? Is that the one?
Yeah, that is. I mean,
Okay.
this is exactly vanishing gradient problem.
Okay.
That is also, described in while we use RNN. But
Okay.
in RNN also we have, somehow this is related with this RNN as well.
Okay. Okay. Thank you, sir.
Yeah.
RNN stands for, sir?
Recurrent neural network.
Recurrent
I
neural
think.
networks. But anyhow, it is because of this repeating nature of these neurons. Okay, so this, as he pointed out, this is technically called as vanishing gradients problem. So this prevents, our network to, getting deeper. Okay, so if you have more than 4 to 5 layers, then weights in the first layer never receive the gradients because of this one. So after observing this, people, changed the activation from, they come up with the ReLU activation, and then they have seen even if you make the network deeper, let's say 10 to 20, then the gradients simply flows across the network. Okay, but if you make your network still deeper, like 50 or 100 in the case of ResNet and other nets, you once again encounter this vanishing gradient problem for various reasons. So they come up with different strategies like residual connection that you will learn if you go through, various resources. But all these strategies are centered around this concept vanishing, how to, mitigate the effect of this vanishing or reduce this effect of vanishing gradient problem. Okay, so that's the reason we go with different activation functions. I mean, this is the core reason. Okay. Okay, where's that? Okay, now we move on to feed-forward neural network, but I hope you all know what is neural network in general, right? Or do I need to recall that, or can I skip this and move to Colab? Or can
we have had a basic of neural network in MLT, but those who have not taken MLT might not know about it.
Yes, sir. A brief introduction would be good.
Okay. Okay, so now we just talked about a single neuron. Why not we stack the neuron, right? Why not we just make a network of neurons? So that's where this neural networks pitches in. Okay, so I just arrange the neurons in a particular order, so I have a network of neuron. Okay, once again the input is going to remain same. I have x1 to xn. So I have, and then in neural networks we have this terminology like hidden layers, we call this, right? We have input layer, which is an input in itself, and then output layer, which produce this prediction, and in between these two we have hidden layers. Okay, so we use this letter L, but you can ignore those things. I have taken this from the lecture slides. You can ignore these notations, L, all these stuffs. Okay, so in this case we have 2 hidden layers and 1 output layer. Notice that all of them are single neurons. Okay, all these circle denotes neurons, and all neurons, take a set of inputs as vector of inputs, and for each one we associated weight with it. The concept remains same. Okay, there is nothing new other than creating the network out of it. Okay, and once again we have this linear part, and it is always good to divide this entire computation into 2 halves. One is the linear and another one is non-linear, and sometimes we call this as pre-activation and activation, different terminologies, but it implies both. Okay, so A1 we denote this as a linear component. Simply AI is equal to W times X or W times H. Okay, so you notice that what so I have an input X. Okay, and then for each neuron we have W, and all these inputs are connected to all the neurons. Okay, so X1 is connected to this neuron, and also this neuron, and also this neuron. So if I have K neurons in this layer, then X1 is connected to all the neurons in this hidden layer. Okay, and X2 is also connected to all the neurons, and Xn. All the inputs are connected to all the neurons in the hidden layer. So for this reason, it is also called as fully connected layers. Fully connected layer. Okay, what does that mean? The inputs from the previous layer. Okay, it is a direct input. If I take this hidden layer 2, the input to the hidden layer 2 is the output from this hidden layer 1. Okay, the output from the hidden layer 1 is also a vector, right? So all these outputs are connected with all the neurons in the hidden layer 2. Okay, that's why they term it as fully connected. So we use see this definition more often. Okay, instead of calling it as multi-layer perceptron or something like that, if I just have 2 layers, okay, and if I use this terminology fully connected layer, meaning that all the neurons in this layer is connected to all the neurons in the other layer. Okay. Okay, now we have to define the weights, right? So the learnable parameters. Once again, the definition remains same, the concept remains same. Now instead of weight, now the weight is a matrix, because if I have just single neuron, right? I think it's better to draw the diagram. So if I have single neuron, I have x1 to xn, right? Maybe I can switch to this. Okay, if we have single neuron, then we have input x1 all the way up to xn. For each of these inputs, we associate weight with w1 to wn. So we can write this as entire computation as a dot product. Okay, I'm just focusing on this linear part. So the entire computation is a dot product. So w is a vector transpose and x is a vector. Okay, this is for single neuron. If I have another neuron, then once again all these inputs, right, x1 to xn, will also be connected to this neuron as well. Okay, now we have to associate a different weights. We can't use same w1 here. So now I have to use different indices. So this becomes w11, w1n. I use this as w maybe 21, w2n. Okay, so we can pack and denote this entire layer. Let us assume my input is a vector x, which is a column vector, and this is a dot product, right? So the weights associated with this particular single neuron are arranged as rows. Okay, I arrange this as w11, w12, all the way up to w1n. These are all the weights associated with the first neuron, and w21, w22, all the way up to w2n. This row actually denotes the weights of second neuron, and if I have m neurons, then it is going to be wm1, wm2, all the way up to wmn. Okay, so this entire matrix vector product. Okay, so this is an input layer, but in the hidden layers, the input to the hidden layer is simply the output from the previous layer, right? h1 to, let's say it could be hm. So my input is always going to be a column vector, and this matrix denotes the weights of all the neurons in a particular layer. Okay, so it is simply a matrix vector product. So you recall that during the beginning of the session, I said deep learning is equal to deep neural networks, and deep neural network means it's deep matrix vector product. Okay, so if you multiply this w and x, then it will gives you a vector as an output, right? So it is an m by n, because m neurons are there. This is n by 1, and then you multiply this, then it gives me an m by 1 vector as an output. Okay, let's say this is my h1. Then this h1 is an input to the next layer. Once again, the weights in the next layer is represented as a matrix. So it's just a chain of matrix vector multiplication, but the output from this matrix vector multiplication is actually passed through a activation function. Okay, you remember that. Okay, again, once again, maybe for where is the eraser? This one. let me denote the output by Z1, or maybe with respect to the notation used in the lecture, this is A1. Okay. So matrix vector product, and it gives me a vector as an output. The size of this vector is going to be m by 1. This is a linear part. Then in neuron, there is another half, which is a nonlinear part, which takes this A1 vector, and then we applied some nonlinear function element wise. So now this A1 contains m elements. So for each element we pass, if it is a sigmoid, I have, let's say 1, 2, 3, then I pass this sigmoid element wise to this function, then whatever the output it gives, I store it the value here. Okay, that is going to be my H1. So it is an element wise computation. So this process repeats. You add next layer. For the next layer, input is going to be H1, and we have a weight matrix associated with that layer. Again, matrix vector multiplication, then you pass it through the activation, that becomes H2. So it's an iterative process. Okay, so you can make it deep. So eventually, if you, from the big picture, you can see that it is a matrix vector multiplication passing through a nonlinear function. Okay, does it make sense? Is that clear?
Yes, sir, it is clear.
Sir, what would be the initial values of all the weight values?
They are randomly initialized. Let's say Gaussian distribution, but there are some initialization methods, but for now you can think of they are randomly initialized.
Okay.
All the initialization are random, but there are some tricks, that's all. Okay, any other question? Because I'm going to make use of this, I'm going to follow the same notation when I write the code in Colab.
Sir, how do you differentiate between weights of one layer to weights of another layer? You have to put some notification, right? Some notation on top of W.
Yeah, if you bring in the layers into picture, then there will be 3 indices instead of 2. But that's not really required. Maybe if you want to study something, then something analytically, then you can bring in, let's say I use I, J, K, okay, and where K denotes a layer which can vary from 0 to L minus 1, and then J denotes number of neurons in the second hit. If I have 2 hidden layers, then it denotes number of neurons in the second hidden layer. Then I denotes the index for the number of neurons in the first hidden layer. So we will have 3 indices, but that's not typically required in our, if you really want to just write a code.
Okay, sir. Understood.
Yeah. Okay. So let me quickly go through a numerical example so that you understand everything clearly. Okay. Yeah, so this just denotes how things happen. So now it's a time to introduce this softmax function. Okay, since it is a classification problem, the activation function in the output layer is softmax. Okay, I will talk about what is softmax now, and this is going to be a typical setting when you develop a deep learning or in general any machine learning model. So we start with the data, and the model is now just nested function. Okay, and then we have parameters W1, W2, W3. If I have k layers, then I will have W1, W3 all the way up to Wk. Okay, then it's a gradient descent, but there is a difference. The gradient descent is now extended in a clever way, so we call this as back propagation. Okay, if it is a single neuron, we say it's a gradient descent, but when you extend this to layers of neurons, then it becomes back propagation. Okay, yeah, so you can use mean square error loss, but in general, if you are using classification problem, then softmax is better. Yeah, let's forget about this binary now. Yeah, so let's take quick numerical example. Let's assume I have.
Sorry, sir, you mentioned about if back pass. Can you just repeat that last statement? I just missed that. I was looking at the
back propagation, right?
back propagation.
It is a gradient descent. No, the gradient descent algorithm computes the gradients. If I have a single neuron, that's fine. But when I connect a network of neuron, how do you make use of this gradient descent algorithm? Okay, so that's where this back propagation actually pitches in. There is a slight difference, important difference between back prop and gradient descent, but that's not, we need not to discuss this now. Okay, let's say I have a vector of size 3, x1 to x3 and some numbers, and then let's say I have W1 matrix. And if I denote this X as a row vector, then you just, all the columns denotes the weight matrix. Okay, so you just multiply, and these are all biases. Okay, so what you are seeing here is bias. So for each neuron, even in a single neuron, we have one bias. So if I have m neurons, then each neuron has its own bias, so there will be m bias. Okay, then I have to add these values, and bias are also, the values for the bias are also randomly initialized. Okay, so in the forward prop, it is simply matrix vector multiplication passing through an activation. So you can use any activation. If you use sigmoid, then you can see all these values. You go all the way up to the next layer, and finally we end up with something called as softmax. So why we use softmax is, when we have a classification problem, if I have, let's say I have 3 classes, 0, okay. I have 3 classes, 0, 1, 2, and do you know what is one-hot encoding? How many of you know that? Or is there anyone
Yes, sir.
who doesn't?
We have that
Yes,
in
sir,
MLP.
we know that.
Okay, so I hope all of you know that. Okay, so for classification problem, it makes sense, in order to see these classes as a single probability distributions. Okay, so that's why we go for one-hot encoding. So you can map this class to one-hot encoding, so that 0 is mapped to 1, 0, 0, and 1 is 0, 1, 0, and 2 is 0, 0, 1. So you can see this as this single row as a concentrated distribution, right? So I have probability exactly equal to 1 at this index, and for the rest of the values, it is simply 0. So when I make a prediction, in fact, what I want is, I want a probability distribution. Okay, so this is my y ground truth, but when I compute y hat, I also want to compute the probability distribution. So typically, let's say the prediction for this particular class, okay, 0th class is 0.8. I want something like this. For the next class is 0.1, and the other class is 0.1. Okay, so now this is a correct probability distribution, right? Because it sums up to 1. And this is a kind of takes away ordering in the class. If you use mean square error, then there is, in the class label itself, there is an order. So we don't want that. So in order to avoid that order, we convert this into one-hot encoding. And then we can see this one-hot encoded labels as probability distribution. And to match this probability distribution, we want the output to be a probability distribution. Okay, so that when I sum up all the prediction for each class, then it should result in 1. Okay, so if I have a neuron, right, I have a neuron here, some values are coming in. Okay, then how do I ensure, right? Maybe I might have some value, right? If I don't use softmax activation function, let us say the output from this linear part of this neuron is something like this, -5, and then 6, and then 10. I know by looking at this number, argmax is the correct prediction. So whatever the highest value I get, I can say the index of this, and this is the prediction. But since I'm using this probability distribution as a measure, then I have to convert this into a proper probability distribution. Okay, that's where this softmax actually pitches in. So softmax is simply you're taking e power, okay, say for example, the first value is computed something like this, I take e power minus 5 and then I simply divide this by all the element, e power minus 5 plus e power 6 plus e power 10. Okay, and then for the next value, I compute e power 6 divided by e power minus 5, e power 6 plus e power 10. Okay, so we can just repeat this for all the classes. And finally, we end up with, the probability distribution. And because of this, okay, we have to use cross-entropy loss, because the cross-entropy loss captures the difference between two distributions. Okay, how two distributions are diverging, how close two distributions are. Okay, and if you really want two technical details, you can study about KL divergence, okay, which actually talks about this divergence between two distribution, and from there the concept of cross-entropy emerges. Okay, and this is the reason why we go with softmax activation function. Is that clear?
Yes, sir, clear.
Okay. So even if you have some confusion, I hope if you go through, the rest of, there are plenty of articles, all of them should make sense. Okay. Okay. So now we have softmax, and then the output is a probability distribution, and then we just compute how far these two distributions are, from each other by using this cross-entropy loss. Okay. And once again, if you refer to the Pytorch documentation, you will see some cross-entropy, negative log likelihood, different terminologies. There are subtle differences between these two, but once you refer the documentation, things becomes clear. Okay. Okay, so now let's switch to collab. I think we are a bit late. Let me try to. Okay, so are you able to see the collab?
No, sir.
No, sir.
What are you seeing now?
Your browser window. You might be
No,
sharing the
sir.
window only.
That slide window.
Okay, I got it. I forgot to stop. Okay, then. What is that? Okay, this is the same collab that I shared yesterday. Okay, do you want the link? I hope the same link should work, but once again, I'm sharing it. Chat. Yeah, Snehal, that's right. We take one hot encoding as probability distribution. Oh, I think, sorry. So I'll share the notebook in the chat, link to the notebook. Okay, there is a question. Is there any scenario where sigmoid is still preferred over other activation functions? Yes, in there is a network called RNN, right? A recurrent neural network, and a variant of RNN is called LSTM and GRU. So there they use some strategies like concept called as forgetting the input or something like that. So they want to forget it, right? So in that sense, they use this sigmoid activation function. Okay. So inside this LSTM cell, they use this tan H and sigmoid. So instead of sigmoid, people go with tan H because of this symmetrical nature. And also it is centered around 0. Okay. Okay, so I quickly go through this notebook, and you may not need to type it at your end. I just finish this up, and then you can do all this on your own. Okay, just Okay, let's load the data. So by the way, are you able to access this Colab?
Yes, sir.
Okay, so in the last session, we discussed enough about this data set. Now let's create a neural network. So in Pytorch, no matter what neural network you want to create, okay, it could be a simple single neuron, or it could be a multi-layer perceptron, or it could be convolutional neural network, or whatever the network you want to create, you end up using this torch.nn module. Okay, so I'm using something called as torch.nn. And this is the core module which provides way to create any type of neural network you want. Okay. And for the optimizers, we have different types of optimizers. Once again, you can access these existing, I think Pytorch provides about 20 types of optimizers, and these are all available in this module of Optim. And of course, I'm using these SKLN metrics for some, just to compute something. Okay. And for the time being, I'm avoiding this data loader because I want to illustrate how to create a neural network and how to train it. And instead of taking 50,000 samples, which takes a lot of time to train, I'm just going to take 100 samples. Okay, again, just to make things simple. The process remains same.
So what is that torch.optim?
Yeah, that is a module which contains different types of implementation of optimizers. In deep learning, we have to compute the gradients, right?
Yes, sir.
So to compute the gradients, we call that procedure as optimization, the entire thing, the weight update rule, right? Compute the gradient and then update the weight or the parameters, right? So
Okay,
that
sir.
updation is actually done in the optimizer. The gradient is computed first, and then the optimizer make use of those gradients and then update the weights.
Would each of these optimizers with different gradients have different learning rates?
Not about the learning rates. The way they move on the surface, right? So the difference, the main difference between different types of, or the main metric that you might use to evaluate different optimizer is convergence. How fast it converge in the sense how fast it reduces the loss to zero, right? So
but
if you
they
use
all use gradient.
Yeah, they have to use the gradient of the loss with respect to all the parameters.
Then what really determines the speed of convergence?
Yeah, that's what the difference, but that's too technical to talk about. For now, you can just say the input to the optimizer for all the optimizers is simply the gradient, and the different optimizers make use of this gradient and in a different way. Say, for example, in SGD, a stochastic gradient descent optimizer that you may all be already be familiar with. Here, this optimizer considers the gradient computed at the current time step, but momentum-based optimizer, keep tracks of the history of gradients. It make use of the current gradient and also the previous gradient and also the entire history of gradients, so that it moves faster than the stochastic gradient. Similarly, Nesterov accelerated make use of the history of gradients. Then if you go with Adam optimizer, then it makes use of the history of gradient and as well as it makes use of the additional parameter, okay, that actually pushes the trajectory of this parameter search in a particular direction. Okay, so this just, the conceptually you can think of like this. I know it won't make sense right now because you have to, know a lot of details in order to make sense of all these statements.
So here data type equal to torch.float32. Is it necessary to mention?
Yeah. So as I mentioned in the previous session, right? So Pytorch demands, a data type for a particular operation to be in a particular, it should be torch float 32 if you want to multiply a matrix and the vector, right? And it has to be, type should be a long for a particular operation. Okay, so once again we have to rely on the documentation, and there are reasons why they impose these constraints.
Okay.
Okay, now I'm just taking first 100 samples, and I just want to ensure that the training sets are shuffled randomly. So the first 100 samples contains all the classes. Okay, samples belongs to all the 10 classes, and the range of the image is naturally is from 0 to 255, but neural networks are sensitive to the scaling. Not just neural network, it could be perceptron or whatever. So we have to ensure that the input should be in the range of -1 to +1 for proper learning. So I am naively just dividing it by the maximum value. Okay, so this NN dot module. So whatever the network you create, you have to first inherit this NN dot module. Okay, so module here refers to layers. Okay, in Pytorch, these terms are interchangeably used. Module means it is not Python module, it is a layer in neural network. So we say it's a hidden layer, right? Similarly, in convolutional neural network, we have conv layer. So the layer in TensorFlow, they call it as layer, as is, no problem. But in Pytorch, they call it as module. So I want to create a neural network. I'm just naming it as feed-forward neural network. Okay, you can name it as MLP or whatever you want. And I have to inherit this NN dot module. So this NN dot module takes care of a lot of things behind the screen. So first you have to inherit this, and then you have to define this construct method. Okay, you have to define this init method, and then in the init method you have to define all these matrix vector product. Okay, whatever the operation that involves with the parameter. In this case, it is in a MLP, it is simply a matrix vector product. But if you go with some, let's say, convolution operation, then that is a different operator, right? It's not simple matrix vector multiplication. So you have to define everything in this init method. Or simply put, whatever the parameter in the network, that you use, it has to go with this init method. Okay. Okay. So
why we are dividing xtrend is equals to x by xtrend dot?
Yeah, that's what I said, right? So xtrain initially it's an image, right? So the image values can take each pixel in an image can take value from 0 to 255, the intensity of the image. So when it is 255, right? If you are using neural network, the input to the neural network should be between -1 to +1. Okay, because that's how, otherwise we run into many problems. So we ensure that the inputs are in this scale. So for that, we divide this by the maximum value in the input.
So is this like normalization?
Yeah, you can think of it as normalization. Yes.
So this will be between 0 and +1.
Yeah. So if the input is, if all the elements are between 0 to 255, then after dividing this by xtrain.max, it will be in the range of 0 to 1. Okay, shall I move on?
Yes, sir. What is?
Okay. So now we inherit this init method as well. Okay, these are probably I'm typing mistakes. I think I just copy paste here so that we can run quickly. Otherwise, it's going to take a lot of time. Okay, so you just pay closer attention here. In neural network, we define A1 as W times X, right? So we also said the neuron is composed of two components. One is the linear component that we denoted by AI, and the other one is the nonlinear activation, right? With that we denoted by H. Okay, so to define this linear component, we call this NN dot linear. Okay, and then I know the input, the size of an image or the shape of the image is 32, 32 height and width, and there are 3 channels, and I'm going to flatten this out. So when I flatten this out, then the output vector will be of size 32, 32 by 3. So that is the input dimension, 32, 32 into 3. It will be around some 3000. Okay, and I'm going to use 1024 neurons in my first hidden layer. So that's what this 1024 actually says. Okay. What is that? I am that name Xcali draw. Okay. So here we are defining something called as NN dot how NN dot linear, and then I am defining 32 into 3, 1024. So what does that mean? So my input X is now, I've just flattened the image into a vector of dimension. So it will be around 3000. So I'm just putting 3000. Okay. And then I'm defining 1024 neurons in my first hidden layer. Okay. And the weight values are simply, can you tell me what will be the size of this weight matrix?
1024.
1024 into 1024.
1024 into 3000.
1024 into whatever the input, right?
Yeah.
Okay. And then also additional bias. So bias size, it is equal to number of neurons. Okay, it's 1024. Okay. So when Pytorch execute this statement, internally it creates all this W and B for us. Okay, we are not directly defining it W and B. If you really want to take control of W, and if you really want to control the values for W, then you can do that, but oftentimes it is not necessary. Okay, therefore it is taken care by the this module itself. So you just need to define linear, then you just pass what is the input dimension and what is the output dimension, and it could be the size of this matrix could be inferred from these two values. So it creates this parameter matrix, and then somehow it keep track of all these things. Okay, and similarly, the output is going to be 1024. We know that. So it is an input to my next layer. So that's why 1024. And I just want to create 2 layers. And output is, the second layer contains just 10 neurons because I have 10 classes. Okay. So whatever, parameters in the network that should go in this constructor method. Okay. Now we know that the network is composed of nonlinear activation as well. So that's what we define in this forward method. So you have to define this init method. Okay, once you inherit NN module, after the inheritance, it is expected that you have to define this init method, and also you have to define this forward method. So this is also expected. You have to use the same name. Okay, this is because this NN dot module inherits all these things. It also defines this forward method, but you need to override this after inheriting this. Okay, so in the forward method is straightforward. That's where the input is feed in. Okay, that method takes in the input and it goes something like this. Okay, And now it is quite clear. You just maybe I need to zoom in. So is that readable? Yeah, now
Yes,
you
sir. Yes, sir. Readable.
just focus on this part. Okay, the forward method takes in an input x, okay, that input from us, the user, right? And then I'm reshaping it, okay, because the input is going to be an image, and then I have to reshape it, which means instead of flattening, I'm reshaping it because I want to ensure the batch dimension as well. You don't need to bother about that for the time being. Just we are flattening this out into 382 by 82 into 3 dimension, okay. Remember, I am passing this input x dot reshape as an input to this A1. Okay, self dot A1 is this linear layer, and I am passing input x to this linear layer. So internally, what happens? The linear layer defines WB and it waits for x2. The linear part is WX plus B. So x has to be fed in, W and B are defined. So it takes this x and multiply that with W and then adds B and then returns an output. Okay, so we will have A1 now. After executing this, we will have A1 now. Okay, which means we will have a vector of size 1024. Then this vector, must pass through the activation function. So element wise. So this vector goes through this ReLU activation function. Okay, so if some of the elements in the vectors are negative, then they will turn out to be 0 because that's how ReLU is defined. If it is positive, they will be retained. Okay, now we have H1, output from the first hidden layer. The output from the first hidden layer is an input to the second hidden layer. So that is self dot A2, right? So I know the output is 1024. So I am passing this. Internally, what happens? It multiplies this H1 with W2 and then adds B2 and then returns H2. Okay, and I am just returning H2. And note that I'm not using Softmax here because I'm using cross-entropy loss. Okay, and studying something in theory differs a bit when you implement it for various reasons. Okay, because the exponential function is really, it takes a lot of time to compute and it is very sensitive, numerically unstable. So we have to take care of all these things while we implement. So keeping that in mind, Pytorch defines different ways of executing this. So we are not going to use Softmax directly, but internally it makes use of this Softmax. Okay, when I define cross-entropy loss. So now we have defined our simple network, which contains one hidden layer, one input layer, and one output layer. Okay, in the output layer, we haven't used any activation for some reason. Now you can create a neural network of any size, right? Because it is simply putting in all these things, defining A1, A2, A3, AK, and then H1, H2, H3, AK, sorry, HK, right? So the extension is straightforward. Same thing is true for any neural network. You can define all the parametric stuff inside this constructor method and then all the activation stuff. Okay, you can see activation doesn't have any parameters. So these things has to be defined in forward method. Okay, so now let me execute this. Now let us
sir.
Yeah.
So like we don't have to define bias somewhere, like Pytorch does that itself, or
yeah, internally it adds the bias as well. So that we will see when we actually look at the parameters. It returns, see, I'm calling the parameters, right?
Right.
So it returns W1, B1, W2, B2.
Okay,
B1
and
bias and
one more question, sir, like how do we decide like how many layers do we need in our model? How many nodes do we need per layer? Like,
yeah, that's once again, no theoretical work on it. It's right. See, if this is your problem, this number of layer is enough. There is no such theory, but there are some theorem like, you might have heard its universal approximation theorem. It talks about width of the network, but not the depth. But anyhow, it is an approximation. But so far, I am not aware of any such theory which dictates this is the number of hidden layers I mean, these are all the number of hidden layers sufficient to solve this problem. We do that by experimentation. But typically what people, of course, there are some practice strategies you might refer to the net, how people, go about choosing the initial network size. And then experimentally, they simply increment the size of the network. But everything eventually falls down to, now we are all, these are all some empirical stuffs. Cross-validation, cross-validation, maybe, as I said, right, in neural network, doing cross-validation is really costly. For simple machine learning algorithms, that's fine. If you have really small data set and small network, that's fine. But for neural network, no one goes with this cross-validation. Maybe in the inference time they can do, but during the training for hyperparameter tuning or anything, they won't use that. Okay, so now let's instantiate this. Okay, and for some reason, I just want to see the weight values in the network so that you can load the weight values using this. Remember, I instantiated this FFN. Okay, so everything is there assigned to this instance model. Then the model has a lot of methods. One method is parameters, which returns the parameters of the entire network. So since I know, I'm aware of how many parameters are there in the network, I'm explicitly writing all this. Okay, in fact, it returns the list. So I know how many parameters are there. I'm writing this explicitly. Okay, W1, B1 and W2, B2. And for visualization purpose, right, the weight values could be negative. Okay, that is fine. But when I want to visualize this, in this case, I want to visualize this as an image, and image values has to be positive or non-negative. So what I do is I just use this, scalar transform, just to ensure that the values are, in the range of 0 to 1. The weight values are in the range of 0 to 1. The reason why I'm doing is this, I just want to see after training my network and whether the weight, the parameters, are learning any patterns. Okay, so that's an intent. Okay, so now
so what is the W1 dot detach?
That needs a greater explanation, but I'm just telling it right now. So when you create a network, this W1, B1, W2, B2 are all variables which requires gradients, right? So we need to compute the gradients for these parameters. So internally, what Pytorch does is it creates a computational graph. So wherever you set required grade so when you create a tensor, like using torch.tensor, typically there is an optional argument where you can set whether this particular tensor requires a gradient or not. Okay, so if I set required gradient equal to true, which is the case for all the parameters in the network, then it adds this parameter to the computational graph. Okay, so I don't want to disturb this computational graph. I just want the values of this computational graph. So when I call this w.detach, it actually detaches this parameter from the computational graph and then convert this into NumPy. And this has to be done again for various internal implementation reasons. Once again, I have to keep saying, so refer to that GitHub link that I shared where I, discuss all these computational graph stuffs in detail. But it requires an understanding about the back propagation. So if you understand the back propagation, then you can understand this computational graph as well. For now, you just, take this answer just for granted.
Sir, in the weight vector, we are using the min-max scalar, right? So then how it could be in the negative sides? The range of min-max will be 0 to 1, right?
Yeah, so see, this I'm doing just for my purpose. I'm not changing the weight values of the network. So I just want to see, display the weight values, but just for displaying purpose, right? I want to see it as an image. That is a restriction. So image the pixel values cannot be negative. So just to, compensate that, I'm doing this scaling. I'm not actually changing the weight values of the network.
Okay, got it.
Just for visualization purpose, I'm doing it. Okay. Okay, so we are real close. So I just copy pasted everything. So here you can see cross entropy loss that is defined from NN dot. Once again, coming from NN dot module, we have different loss functions. Okay, and I'm optimizer. I'm going to use this SGD. Okay, so the stochastic gradient. I'm setting momentum factors equal to 0 so that it is stochastic gradient. Otherwise, it is a momentum based gradient descent. Okay, and you just look at the arguments passed to this SGD. Okay, we have to compute the gradients. So gradients are computed internally in the computational graph, and I want to update the parameters using this gradient. Okay, so I'm passing these parameters as an input to this SGD, and gradients are available already. And then this optimizer takes these two, the parameter and the gradient of it, and then make an update based on the type of the algorithm. In SGD, it is straightforward, W minus eta, and then the gradients. If it is Adam, then the process is quite involved, and then it will be taken care by the implementation. We don't really need to bother. And typically we set the learning rate to a very small value. Otherwise, in deep learning, there is a high chance that even a bit of increase in learning rate lead to, divergence. Okay, so it is always safe to start with very small learning rate. Okay. Okay, so you just ignore all this. Okay, this has nothing to do. I'm just initializing this to keep track of something. So only thing.
Mayday. Mayday.
With that.
Mukesh, can you please mute your mic?
Okay. Okay, I will share the G form. Many are asking for that. Let me complete this. This is the crucial step. Okay. Now we are using stochastic gradient descent, and I am going through all the samples one at a time. And warning, this is not the right approach. Just to illustrate how the entire thing works, I'm just doing this. I'm just going through, creating a for loop and going through this. If we make use of data loaders, then the process becomes too simple. Okay, now I'm just making it a bit complicated. Okay, there are two loops. One is, epoch, and the other one is, we call it as an iteration. Okay, so I'm just going through, the X-train contains now 100 samples, so 100 times I pass one sample at a time. Okay, remember, model is FFN. I'm passing an input to the model. Just once again, you may take a look at here. Okay, so we have instantiated the model. So how do you pass an input to the model? So you can pass this as something like this, X_train. So I'm just passing the zeroth sample. Okay, and yeah, reshaping is taken care here. So I'm just executing this. It produces some output. Okay, so that is H2. And you can see there are 10 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. Okay, so the input to the model is passed by this call method. It is once again defined internally. There is a magic method, def_call, that is also implemented. So you simply pass the input as an argument to this model. Okay, so that instead of X_train 0, I'm just passing the index, one sample at a time, and we are getting an output. And also I want to make the label out of it. So argmax actually takes the label from the output. Wherever the maximum values in the out of 10, the index of it will be returned. So that's what I predict. Okay, then I'm passing this output to the loss function. So the criterion is cross-entropy loss. Recall that the loss function takes two arguments. One is the prediction, the other one is the ground truth, right? So out is the prediction, white train underscore I, of course, don't bother about this none. We are just adding additional dimension. Y_train I is a ground truth. Okay, these two are passed as an input to this cross entropy. Then it returns the loss value. And the important step is now I'm calling this loss dot backward. Okay, so far the forward propagation is executed. Okay, we have computed the forward propagation, and then we computed the loss. Now we have to start compute the gradient. Okay, so internally a thing called as computational graph is constructed, and every process in the operation in the computational graph is executed. Now the moment you call loss dot backward, it computes the gradient for all the parameters. Okay, it just computes the gradient and it retains it somewhere. When you call optimizer dot step, then it makes use of the gradient and update the parameter. Okay, and then it multiplies with the learning rate and update the parameter values. And then I have to do this zero grad. Okay, because I'm using SGD now, I want to update the parameters for each sample. Okay, not batch of sample, not for full samples. So for each sample, I'm going to update the parameter, and then the process repeats. And these are all just to keep track of the loss value and accuracy value. So the 4 lines of code, okay, completes the entire process. We have a data set, we define the model, we feed in the samples to the model, compute the output, and compute the loss function, and then compute the gradient and update the parameters. Okay,
so sir, like whenever you are calling this optimizer dot step, right, that time you are computing the parameters, right?
Update the parameters.
Updating the parameters, right?
Yes.
So now these updating the parameters, this is the first order updates, right? So that means okay, now say for example, like if you want to do the second order update also, so is there anything like by default or like some configuration, or you need to write the backprop in that case?
No, when you go for second order, in the case of LB, FG, some algorithms are there, the update is quite different. It is not something straightforward because you need to keep track of few other things as well. People, additionally define something called as closure function. Okay, that I don't want to go into detail, but if you refer to the documentation, you see for second order optimizers, they define something called as closure, and then they use this step method as well. Yeah, I mean, it is something different for second order optimization algorithms.
Okay, so it is not straightforward, because you need that Hessian, you need the Hessian matrix actually in mathematically.
Yes, but for deep neural networks, computing Hessian is not numerically stable.
Okay,
so they go with the gradient only.
Okay.
So one doubt, when you're doing the optimizer dot step, you're just updating the weights you're telling. What is that step optimizer dot 0 underscore grad?
Yeah, it is okay. Okay, I shared the G form, so many are asking for that. Let's say I have 3 samples, okay, x1, x2, and x3. And then I make use of this sample x1 and then make a prediction y1 hat and then compute the loss, okay, and then compute the gradient of the parameter, gradient of the loss with respect to the parameter w. Now I have choice. If I use SGD, okay, stochastic gradient descent, meaning that for each sample, I'm going to update the parameter. So I compute the gradient for this sample and immediately I use this to update the parameter W eta. Then I update the parameter, okay. But if I want use batch gradient descent, okay, meaning that instead of relying on a gradient of a single sample, then I compute the gradient for this one, y2 hat, and then compute loss, and then I compute the gradient of the loss with respect to this parameter for this sample as well. Okay, so if I use dot 0 grad, okay, then it deletes all the existing gradients. Okay, so for SGD, for each sample, I have to do this. But if I use batch gradient descent, then I have to retain or in other words, I have to accumulate the gradients for the same parameter for different samples, right? Or for all the samples in the training set. So which means if I don't use 0 grade, then those gradients will be accumulated. Then I can make use of them, accumulated gradient, to update the parameter.
Okay, so thank you.
Okay.
Hello, sir.
Yeah.
Actually,
Okay, let
the
me
learning.
execute this. Then if you
Hello.
have, yes,
Can you
please.
hear me, sir?
Yeah, I'm able to hear you.
The learning rate is also decided by the module value, or is there a provision that we can
No,
give the
learning
learning
rate
rate,
is
sir?
that learning rate is the hyperparameter that we need to set. So either you can
So
use
where are we
this learning
setting
rate
here, sir? In this code, where are we setting the learning rate?
here, LR.
Okay. Okay, sir. Yeah, got it. Thank you, sir.
Yeah. Where is that? Okay. Okay, now we defined our model. We just need to train it. Since we have only 100 samples, right? We can train it quickly. And then I'm just keep track of this loss and accuracy just to see whether the model, I mean, whatever, when you develop a model, remember that many things can go wrong, okay, without your attention, right? Because those could be semantic errors. So it's very difficult to debug. So oftentimes in practice, what people do is that I have a deep network. So if the deep network, I take only a subset of samples, in this case, it's 100. So if my deep network is able to overfit my 100 samples, okay, then whatever the thing I have defined is most likely correct one, okay. So that's a strategy that people follow, and also it makes sense. Yeah. So let's see what's the loss value. I hope. Okay, so you can see that the loss decreases. Of course, since we are using SGD, it increase, decrease, increase, decrease, but eventually it approaches, maybe, I'm not sure, but near zero, right? Because the network is really, which contains 1024 neurons and then 10 neurons, right? So this 1024 neuron must at least overfit these 100 samples, okay, that is expected. So we can say whatever that we have defined so far is semantically closely correct, okay. Still we are not sure unless we train the model and see for the entire data set, but we just hope that it might be true, okay. Now I want to visualize the updated parameters. So once again, we repeat the same step. We just load the parameters and then display, is there any changing pattern, okay. Then I can see, of course, this still not makes sense. I'm not seeing any pattern emerging out of it. Maybe if we run it for 100 epochs, and also the loss becomes zero, okay. So running it for more epochs doesn't make sense. So maybe if we use some 1000 or 2000 samples, we can perceive some sort of patterns, okay. Of course, we can't make sense of it, but what we can say is that the parameters are, properly updated. It is learning something, okay. At least it is not sitting ideally, it is learning something. So we can ensure that, okay. Yeah, so, in typical machine learning setting, we first divide the data set into train and test, and we also assign train to validation, and then we do all this proper stuff. But I hope that you already know the entire, if you have already done machine learning practice course, you are well accustomed with all this process. So I am not focusing on this aspect. Instead, I'm just focusing on the algorithmic aspect. Once you understand that, then you can follow the same. Not a big deal, right? Is this today's? Yeah, I'm not sure. Whatever I shared is, I'm just getting it from some spreadsheet. So I hope that is for today's session. Okay, that's all from me. So if you have any doubts, you can ask me. Tomorrow I try to cover CNN. CNN is really big. I'm not sure whether I'm able to cover both theory as well as coding, but I do my best. I keep reiterating it. So if you want to dive deeper into deep learning, right, these sessions are just introductory. You can follow the deep learning course or whatever the course you want to follow. And also you can follow the notebooks I shared in the collab. Okay. Okay, thanks a lot. Yeah, if you have questions, you can.
Thank you, sir.
Yeah.
Thank you, sir.
Yes.
Like the difference between these different libraries like Pytorch and Keras, or like do they matter as a beginner, or like?
No, it doesn't matter at all. You can start with anything.
Okay, so like the idea is same, the basic concept is same for.
Yeah, see, the tool, these are all just tools, right? So I have some theory, I want to implement it, and these tools support it. So whatever the function I need, that has to be implemented in Pytorch as well as in TensorFlow. Of course, people now are moving to still higher level APIs like Lightning and then Hugging Face based on their need. But knowing, the basic framework like Pytorch and TensorFlow is always helpful, because you can take control of what you are doing. Otherwise, you have to go with the custom models, right? So I would advise you look at Pytorch and TensorFlow and don't go with high-level APIs. As if you really want to go into this field and if you really want to become a professional in deep learning, then you have to understand the basic TensorFlow and basic Pytorch. Don't start with Keras. Okay, if you want to do some project for some reason, of course you go ahead with Keras. But if you want to do research or something very high-level production, then start with basic APIs, NN.module and TensorFlow.
Okay, sir.
Hello, sir.
Yeah.
So you told that at some point the model, the divergence happens. Can you just explain, a little bit on that, sir, where actually the divergence, happens?
So I used the word divergence in the sense that, so you may often see, even if you use batch gradient descent, here I use stochastic gradient descent, so the loss oscillates. Typically, we expect the loss to decrease, okay? But in SGD, it is okay if it oscillates. But let's say you use batch gradient descent, but you're still observing the loss is increasing, okay? Oftentimes you see that. Okay, typically you want the loss to decrease, but even if you wait for some 10 epochs, the loss keep.
In general, doesn't the gradient descent actually reduces the, errors, sir? There is a chance it increases also.
No, the gradient descent, one possible reason, see, I compute the gradient and I want to descend, but if my learning rate is not proper, then I may jump into the ascending direction.
Okay.
So the learning rate also decides whether the loss increase or decrease. So when you observe the loss increases, one thing that you can do is you reduce the learning rate as small as possible, maybe 0.00001, and then see whether it decreases. Then you can ensure, yeah, okay, it is the problem with the learning rate. But as I mentioned, if something is not working as we expected, in deep learning, there are many possible reasons. But only our, our understanding about the algorithm helps us to debug why something is not working properly.
Sir, also the loss. Hello.
Yeah.
So also the loss function in case of deep learning is not convex, so it's not guaranteed to always like get to the minimum value, right?
No. It is not guaranteed the global minimum. It reaches the minimum.
Yes. My bad. Yeah. Yes, that's what I meant. Global minimum. Yes.
Yeah. But we expect the loss to decrease. It might end up with either it remains same or it end up with some bad local minimum.
It's on the initialization, right? Which local minimum it ends up in.
Yeah, it depends. Lots of factors. It depends on the initialization, where you are starting your algorithm, and also the optimizer and the learning rate. All these things decides where it ends up with. And moreover, the problem is that the loss function contains many local minimums, not one or two. The loss function is really spiky. So if you visualize the loss function of deep learning, there are papers. And if you look at them, you see the global minimum is there, but if you initialize randomly, there is a high chance that your algorithm end up with local minimum because there are many local minimums.
Okay.
It's not smooth surface.
Sir, one question could be a silly question. I looked at the entire train path, right? So we have defined it. Doesn't seem to be anything different from what we would expect. So in sklearn, there is a simple, train function. In Pytorch, why do we code it ourselves? We are not doing anything extra.
Sorry, you are asking some sort of fit transform or fit.
We just have a fit and then there's a transform, right? So fit is what we have done so far. But there is nothing extra that we have done. I mean, not that we are doing. Obviously, the network definition I understand. That init part I understand because it's a network and we have to define that. But the train part seems to be the code that we write in MLP anyway. Right? And so why do we, why don't they just, is that just a design decision that they decide that you will do code it by hand?
No. So they want to give, when they make every possible functions, right? So they have given you kind of big grocery, right? So if you want to customize something, then if you know each ingredient in the entire departmental store, then you can customize it as you wish. But the moment they provide some sort of dot fit transform, they modularize many stuffs. Okay, that's what exactly the high level APIs does. So even in fact, I'm heard of, or even I'm aware of, and a package that is built on top of Pytorch, which follows the patterns of sklearn. So you can, I think that is called as Scorch or something. So there, if someone is coming from sklearn background, and if they are accustomed to all the patterns used in sklearn package, then they can straight away start with Scorch, and then the Scorch, in fact, takes the pain away from them. Okay, because from their point of view, they just want to implement some neural network and then want to train it. They don't want to go into the detail. But Pytorch provides this, once they provide all these to you, then you can customize it. That's the reason why we go with low level API. I don't know whether I answered your question properly, but
I got it. Yeah, thank you. So basically, we have more control here. And so in the example, you have kept it simple, but it is possible that we use many different customizations.
Yes.
In practice.
Yeah. So whoever creates, even if you look at the people in Google or Amazon, they also follow the NN.dot module. Whatever the network you want to build, if you, so let's say the Hugging Face is now the most commonly kind of de facto for NLP. So if you want to implement some architecture, if you look at the Hugging Face, and if you just keep track of their source code, and they end up with this NN.dot module, they created everything from this NN.dot module, and then they provided as an abstraction to the end user. So if someone is, someone has a good grasp on this NN.dot module level, functions and concepts, then they have really high control.
Sir, I have one small question. It may be silly, but when you say you have a number of hidden layers, is there any chance, like sometimes from when you're propagating from one layer to another layer, it may skip a layer or something like that? Does that ever happen?
Skipping the entire layer can never happen.
Like say if you have 3 hidden layers, from the first hidden layer, it directly gives all the input to the third hidden layer instead of not using the second hidden layer, something like that. In this neural network design.
That happens when your network becomes really deep. That's what the residual connection does. So in CNN, there is a concept called as residual or skip connections, where they skip, 1 or 2 layers, and then they directly connect with the next layer. That by doing so, they allow the gradient to flow. So yeah, what you're saying is right. So the skip connection is there, but when you have no other option, then having a skip connection is good.
Okay, thank you.
Yeah.
Sir, also, is it a general practice to code the neural networks in object-oriented programming paradigm?
Yeah, it is always a good practice.
Okay.
And in fact, in Colab, we do all this, but when we write a script, we keep different script. We keep the network in one script, and then training part in the other script, and the data in the other script. So scripting is quite different, but for the learning purpose, we can use, this Colab flow.
Okay.
Sir, I actually wanted to pick your brains on a problem I'm dealing with. It's actually a real problem for a very large global CPG manufacturer. Can I just check a few points with you?
Yeah, sure.
Yeah. So I actually come from a consulting, advertising and marketing consulting background. I've been working for almost 20 years now. Now I run my own small consulting shop, and I'm not very interested in all these things. Right? So I've kind of been learning all these things. The challenge we are facing is, so if you see traditional print ads, or any kind of digital ads or print ads or even packaging ads, there's a lot of money which is spent, and a lot of times when you want to evaluate which one is working, which one is not working, there's usually somebody, a designer, or kind of the typical way of doing it is you ask consumers, do you like this pack or this packaging format, right? And they give you some opinion, and there's standard, very evolved, like tried and tested ways of capturing those responses on various scales, and like it, not like it, right? So there's a standard way of doing it, and that will never go away because you need diagnostics, which is not possible through any of these deep learning models, right? Along with that, we've been trying to see if we can use any of these deep learning models, or even traditional machine learning. Why deep learning? Any of these models to perform better than what a human does in terms of evaluation, right? And what happens if we build a network like this, a model like this, is that my costs will eventually go down, because every time I don't have to go back to 200 consumers or 200 or 20 experts and ask them which ones are good, which ones are bad. I can just run it through this model and at least get these are the top 5, these are the bottom 5, and then I can work on it, right? So eventually time and costs come down, right? Provided we are able to build some of these models. Now most of the computer vision models are in the space of object detection, segmentation, all these kind of things, right? It's not really evaluation of packs or aesthetics, right? There is only one, from whatever research I've done, it's called NEMA, which was released by Google, I think a few years back. So what I am trying to do, or my team is trying to do, is basically take some of these established models and kind of use it as is to begin with, and then kind of map the output to the actual scores which the industry is used to looking at, right? So they have a certain way of looking at it. May not be exactly how this will give, right? This gives a probability distribution of what people score on the aesthetic score, but that needs to be converted into something else, right? You can use any of these kernel functions or any kind of mapping to do that. That's secondary. But is there, so one is just use this as is, which is why I was asking that question. If I have to train this model to, let's say, to my situation, right? What are the bare minimum number of samples that require, right? That was the reason why I asked, because getting good labeled data is always a issue, right? Unless, it's a large funded, or, project or a large company, things like that, right? Individuals or even small company, even established companies don't do it because that's not their mainstay, right?
Yes.
So that was the reason. And two questions. One, would you have a guidance on, what are the minimum number of samples we would require, right? For example, I'll give you an alternate example. The same model was used by booking.com, I think, booking.com or one of them, to evaluate so on their website, they put hotel listings, right? So what is the quality of that picture, right? How aesthetic is it? How good is it, right? So they started using this model to evaluate those, and then go back to people who list the things and say that, no, this is not good, it needs to be better, and so on and so forth, right? So that the image is appealing. So I'm trying to do something like that, but in the space of, product packaging and the visual appeal of the product packaging. Now, sorry, I took like almost 10 minutes to give you the entire story so that you're very clear of the objective, because it's very important to know the business objective very well.
Yeah.
Now, my two questions to you, guys, if you can give me some guidance, is one, is there some way of understanding, what are the minimum number of samples I'll require? Or, do I have to first evaluate a few, just do a test run and see how good or bad the scores are? I don't know how to approach it also. Two, have you heard of any other such, neural nets, established models which do this kind of work, which is essentially evaluating the aesthetic quality of images, right? Not, I don't mean by aesthetic quality, I don't mean resolution quality, right? Is it pixelated? Is it good by, I don't mean that. I mean, like, for example, if I show you 2 Colgate packs, okay, this packaging is attractive to me. This is not so attractive to me. Right? It could be color combination, images, all kinds of things. We don't know. The beauty about the deep learning model is it does this abstract feature extraction, which human beings can't do beyond a point. Right? So these are my 2 questions: basic sample and any other models you have heard of, sir. That will be like immensely helpful.
Yeah. So, I mean, the second question is, I'm not aware. I mean, I have seen people have done some aesthetic related things for the face, but not for the packages. But for the first question, when you have a small set of samples to train a model, if you want to train from scratch, then that is not going to be sufficient. Even if you have 10,000 samples for a deep neural network is not sufficient. But what you can do is that you said, there exists an already pre-trained model released by Google, right? On some other related task. So in such a case, what we tend to do is that we do some transfer learning. Okay, people call that as transfer learning. So if 2 tasks are related, okay, in somehow, then what we can do is for one task, there are plenty of labels and images. You train the model on that task. And then for task 2, where you have only few labels or few images, then what we can do is we can take the model trained from task 1 and then remove a few layers, okay, maybe final layers. And then you just make a small change. You retain the parameters as is, but make a small change in the model. And then you retrain it with the small set of samples. So in this way, the model quickly learns the necessary patterns to, solve the task 2 problem. So the transfer learning is, as of now is the, I think it's the solution.
Okay, that was very helpful. Because the first one I'm already doing, this is called NIMA, NIMA. You can look it up, sir. Neural image aesthetic evaluation or something like that. So I'm going to take that. You're saying, see if I can break it down and take out the. So I have to go back to them and say, I need at least 100 packs or 100, with labeled packs. Like I need the actual evaluation score so that I can convert this into that. So I have to go back and tell them, am I talking about 50, 100, 500 or 1000, right? The more I ask, the more expensive it becomes for them. Right? So
so you can start with bare minimum and see how the model actually performs.
Sir, I don't know, this may sound a little unusual. Is it possible for you to share your email ID? Because if there is something if it interests you, I may bother you again later. Is that okay? I'll share my email. You can just write to me if you don't want to give your email ID here. Right? I'll just put it on the chat. Right?
Yeah, that sounds good. Yes.
Thank you so much. Really helpful, sir. That was a very good idea.
Yeah. So in fact, the like in the case of NLP, right? Now we know ChatGPT. So ChatGPT can learn from, there is a concept called as zero-shot learning or even few-shot learning. So where you give a very few training examples, maybe 5 or 6, then the model quickly learns about it. Okay. So that's possible in NLP domain now, but people are exploring the same in computer vision domain by using transformer architecture. Maybe if we look for some transformer based architecture in computer vision domain, then that might be helpful.
Okay, thank you. Made a note of that.
Yeah.
Sir, I've just shared my email ID. If you
I noted it down. Yes.
Thank you so much.
Yeah. Okay, thanks everyone. I think it's now 10:15.
Hello. Sir?
Yes.
Sir, yesterday I was there in whole session, but I didn't notice when the attendance G form we got.
No. Okay.
So what I can do now?
You share your roll number, then I just forward it to the coordinator. I don't know whether the attendance are automatically monitored in Zoom, like in the case of Gmeet. I just convey this to them. So whatever the step they take, that's
actually
the
most of them didn't know that yesterday that the G form has been shared.
Sir. No, I don't know. See, I shared it in the chat, right? So I'm not sure whether, I hope it, it reaches to each one
Okay,
of
sir,
you.
I'm sharing my roll number.
Yeah, that I just forward it to them. So if they have, some way of assessing whether you have attended
Shared,
the
sir.
session or not. Okay.
Thank you so much, sir. It was nice session.
Yeah, thanks a lot.
Thank you for the session, sir.
Should we share the roll
Excuse
numbers
me,
to
sir.
you in DM or the public chat?
Whatever, even if you share it in the public chat, that's fine. I think no one can do anything with the roll number.
Yes, sir.
Excuse me, sir.
Yeah.
Sir, just a quick question. Whatever you are teaching as part of this workshop, is it a strict subset of whatever we'll have as part of deep learning, the degree level course?
Yes, yes. So it's a very basic thing, right? I mean, not basic. So it's kind of, if someone don't want to do deep learning, but they want to make use of deep learning models, then how do they get, started with? So that's the objective of this workshop.
Okay, yeah, got it. Thanks.
Yeah.
Thank you, sir. Thanks for the session.
Yeah, thanks a lot. The many students are entering their roll number. I'm not sure. I just forward them as is.
So actually, initially we were told that attendance would be taken directly from the Meet logs.
Yes, sir, because that's how it
But
happened
later on,
in the
later on,
previous
it
term.
started with the Google form.
Yeah.
Oh, is it? But it's only the students who reminded me, right? So they put, they ask it in the chat, then I got reminded, then go back and get link. I don't know. They said they sent a mail to all the registered participants.
Okay.
Okay,
I'm not
anyhow,
aware of that though.
I just forward all this to them. Maybe we may resort to, if you attended at least for 2 days, or if whoever attended the session, we may take a quiz, right?
Yes, that is also possible.
Yeah. Okay. I noted down all the numbers. Time should extend till 10:30. Why?
For tomorrow's session, if possible, sir.
Yeah. See, even if it is 10:30, there is a lot to learn, right? So we can't consolidate or condense the content. There is always gaps because I have to skip a lot of things to get into different concepts. But yeah, try my best to cover most of the essential concepts about CNN tomorrow. Let's see if it goes to 10:30. I'm fine with that. Attendance time. Okay, I understand. So they are very strict on it, right? Okay, thanks a lot, everyone. Let's see you all tomorrow. Yeah, bye.
Yes,
Thank you, sir.
Thank
Good
you,
night.
sir.
Good night.
It's feel good to train my first model in your session, sir.
Sorry?
Like it's feel good to train the model. Actually, it is being my first model actually, so it
Oh.
feel good.
Okay, then.
Thank you again so much, sir. Thanks for the advice.
Yeah,
See you tomorrow.
thank you. Yeah, bye. No, RNN is beyond the scope of this bootcamp. Even I feel how do I am going to cover CNN, but RNN is quite involved than CNN. Next term, see if in the deep learning course it is there. Okay, so you mean in the next bootcamp? So if you are interested, you take a look at that GitHub. So I tried, if you know RNN conceptually, then you can follow that collab notebook in the GitHub. That will be suffice. But if you want to know the math behind RNN, how back propagation through time works, then that's not possible in this case. Okay, noted, Aditya Maulik. The link for the course content. Or you mean GitHub link? Oh. Okay, I shared it in the chat. Okay, I'm closing it now. Bye, everyone. I think the rest has gone to sleep.